Okay, so on Friday, I'm starting to listen over. On Friday, we did distance time graphs. So say this was one of the graphs that you had. Where are we starting? At the wall. What do? We walk away from the wall for how long? 1 second. Then what do? Stop for how long? 2 seconds. And then we walk towards the wall for 2 seconds. So this is a piecewise function. It's a function because it does pass the vertical line test. Every x has exactly one y. And we can split up this domain. Okay, the domain here is our time. But our domain is split into 3 sections. You said that between 0 and 1 second, we were walking towards the wall. So there is going to be one function rule to define that piece. Then we have another function rule to define what happened between 1 second and 3 seconds. Okay, now I can only be equal to 1 in one place, so I'm going to let it be on the first one. All right, and then we have another function rule to define what happens between 3 and 5 seconds. Okay, so you see how our domain is broken up into 3 pieces based off of the 3 actions that we had? Walking away from the wall, stopping, walking towards the wall. And our domain's broken up into 3 pieces. Well, we can write an equation to represent each of these pieces. Okay? What is the slope of this piece of graph right here? We go up how many? 6 and over 1. Up 6 over 1 gives us a slope of 6. 6 over 1. What's the y-intercept for this piece? 0. So what would the equation be for this first piece of graph? Y equals 6x plus 0. We don't have to put the plus 0. So you would just have y equals 6x when or if our time is between 0 and 1 second. So we're traveling at 6x. Our distance from the wall is 6x if it's between 0 and 1 second, if our time is between 0 and 1 second. All right, let's look at our second piece of graph. This is a horizontal line. What is the equation of a horizontal line? Y equals whatever the y-intercept is. So let's look over here. Our y-intercept would be 6. So this equation would be y equals 6. Now, this makes sense because if, sorry y'all, this little piece is going to bother me. I don't know if it was bothering any of y'all. It was bothering me. If we are between 1 and 3 seconds, our distance from the wall is 6. Okay? And then finally, on our third piece of graph, we have a slope of what? So from here to here. What do we have a slope of? Up 6 over 2. So up 6 over 2. Is this a positive or a negative? Negative. So our slope is -3. What's our y-intercept? That's a little harder to do. Okay, our x-intercept is 5. So let's just pick this point. What is this point? 5, 0. If we have a point and a slope, how can we find the equation of that line? Point slope form. Remember yesterday? Y minus y1 equals m times x minus x1. So we would work that out. Here's your x1, y1. Y minus 0 equals -3 times x minus 5. So that would be y minus 0 is just y equals -3x plus 15. So if you are traveling between 3 and 5 seconds, your distance from from the wall is -3 times the time plus 15. -3 times x plus 15. I'm going to erase all of this now so that I can put my equation up there. -3x plus 15 is what we got. And that's if your time is between 3 and 5 seconds. Guess what? That is all there is to a piecewise function. Okay, we have just written a piecewise function to describe our distance from the wall as related to our time in seconds. Let me pause the recording and I'm going to let y'all ask questions. Okay, so we're going again. Here is the definition for piecewise functions. There is a tiny little blurb about piecewise functions in your book on page 90. So we're going to spend a good bit of time in class on it today and tomorrow. A piecewise function has different rules for different parts of its domain. If you're thinking about our distance and time example, we did one thing from 0 to 1 second. We walked towards the wall, or away from the wall. Then for the next part of the domain, 1 to 3, we stood still, 6 feet from the wall. And then we walked towards the wall from 3 to 5 seconds. So for each part of the domain, you have a different function rule. We're going to start with a notation example. So I'll give you just a second to copy this down. All right, so when we're looking at this example, we have 3 pieces of domain again. You won't always have 3 pieces of domain. You could have 4, 5, 6. You could have 2. Okay, but a piecewise function is going to have at least 2 pieces of domain. This one, again, though, has 3. It's set up very similar to what we had. Let's look at example A. Find f of 7. Which part of the domain does 7 fit into? Less than 5, between 5 and 16, or greater than 16? It's between 5 and 16. So, what is the value of f of 7? 10. That's it. Your answer is just 10. When x is between 5 and 16, f of x is 10. So this one's just 10. Because our function rule tells us that when x is between 5 and 16, that our f of x is 10. Yes. All right, let's look at -3, though. Let's look at -3. -3, which domain does it fall into? X is less than 5. So when x is less than 5, our f of x is 2 times x. So we're going to have 2 times, what are we plugging in for x? -3. So the answer is -6. Thumbs up, sideways, down. Okay, you try C and D. You try C and D. 20 is greater than 16, and so we use the function -2 times x. We plug in 20 for x, and we get -40. And then on the last one, 16. Now you got to be careful. This is greater than 16. Equal to 16 is here, so it is 10. All right, y'all did a great job on that. Let's move on to an example, and you do not have to write this down. An example that you already know. The absolute value of x. Its graph looks like a V. Okay, you see the little V here? So it has 2 parts. If x is greater than or equal to 0, then your y is going to be equal to that number, like the 0.1122. But if your x is less than 0, what happens with absolute value? If you put a negative number in, you get a positive number. So if you're putting in a negative x, you're going to get a positive x. So the rule for x is less than 0 is the opposite of x. If your x is negative, you're going to end up with a positive, right? If your original x was negative. All right, so that's just an example of something you already know that is a piecewise function. Piecewise functions, this one is called the greatest integer function, and we'll talk about it tomorrow. Here's a real life example, okay, shipping rates. I like to buy clothes for my little girls on things like Zulily or Dash of Glitter, like these little websites, and depending on how much you spend or how many outfits you buy, your shipping changes. Okay, your amount of shipping changes. So here's a real world example of that. We're looking at postage, and if the weight is less than or equal to 1 pound, then you pay $2.23. If the weight is more than 1 pound but less than 2 pounds, you weigh $2.58. If it's more than 2 pounds but less than or equal to 3 pounds, you pay $2.93. Okay, this is real world stuff right here. So if we're looking at the graph of that, of course, if it weighed 0 pounds, you wouldn't be shipping anything. So you would pay 0. But immediately, the first little nano ounce you get, you are going to be up and paying $2.23, all the way up to a whole pound. Now, immediately, 1 pound and 1 little bitty nano ounce, you're going to be up here at $2.58. So that little closed-in circle means it's equal to $2.23 at 1 pound, but the next little thing over 1 pound is going to be $2.58. So there's a hole at 1 pound for $2.58, but the next thing over that. Okay? That's also an example of the greatest integer function. Now, this is like the first example we did. Write a piecewise function to represent the graph. We're going to skip it and go to this one. Okay. So, this is everybody's favorite one. Okay, this only has 2 pieces of graph. It only has 2 pieces of graph. But you need to write this down. But we're going to do this one. And this will be all we have time to do today. Okay, so how many pieces of domain does this graph have? 2 pieces of domain. If you look, we are going to have a boundary line at x equals 2. Right here where x equals 2, that's where things are going to change. It's going to be going one direction to the left and one direction to the right. Here is what I would do if I was trying to graph this. I would say, okay, I'm going to make a table for the first part. I'm going to plug in some x values and see what I get for y. How many ordered pairs do I need in order to make a line? How many, Justin? To make a line, how many ordered pairs do I need? 2. I need 2 points. Okay? So, the first x that I'm going to plug in is going to be my boundary point. 2 isn't included. So what am I going to have to do to show on my graph that this point is not included? An open circle. So when we do this one, we're going to have an open circle here. And then we're going to need a number that is less than 2, because this is x is less than 2. So what's a number less than 2? 1. So we plug those in. And we have 2 ordered pairs. We have the ordered pair 2, -1, and the ordered pair 1, 1. Okay, these are our ordered pairs, x and y. So I go to graph that, and I have the point 2, -1, but remember, we're not equal to 2 here, so we have to use an open circle. And then I have the point 1, 1. Now this is x is less than 2, so I'm only going to draw the line to the left of 2. I only draw the line to the left of 2. Because we're doing x is less than 2. And then we'll make a table for x is greater than or equal to 2. We're going to make a table for x is greater than or equal to 2. I want to include my boundary point of 2. Is that going to be an open circle or a filled in circle this time? It's going to be filled in because we've got the or equal to. And then what's a number greater than or equal to 2? We've already done 2. What's another number? 4. Okay, so I'm going to just tell you, if you plug in a 2, you get a 1. If you plug in a 4, you get a 3. So our ordered pairs are 2, 1, and 4, 3. So I'm going to go and plot the point 2, 1 with an open circle. Closed, I said open, didn't I? I'm sorry. Closed circle, and then 4, 3. 1, 2, 3, 4, 1, 2, 3. And because we're wanting to go greater than or equal to, we're going to draw the line to the right. And that is your piecewise function. Now, tonight,